This particular series is called LLM Makerspace. My name is Jim Dowling. I'm CEO of Hopsworks, and I'm going to go through building an LLM application. And the LLM application I'm going to build today is an application to index private PDFs, so PDF files, so that you can search them. All right, now, this is something you may have seen before. I have this website here called PDF AI. It provides exactly this service, which is really nice. The difference is we're going to do this with open source, and it's something you'll be able to build yourself and try it out yourself. So if you have, for example, private PDFs that you're not able to upload to pdf.ai for compliance reasons, then this might be something of interest to you. If you're just interested in learning how to build an LLM application, I really hope this will be of interest to you. How it's going to be a little bit different to maybe what you might expect. So if you've heard of vector databases are a way of storing what we call vector embeddings. You could take a PDF document, chunk it up into smaller parts like paragraphs or pages or sentences, and we can compute embeddings from that data. We're then able to find similar text. That's one of the technologies we're going to use, but we're not going to use one of the well-known vector databases, so Pinecone or Weaviate or something like that. We're going to use Hopsworks Feature Store, which has in 3.7 recently released. It now has support for approximate nearest neighbor search, an ANN index. So we'll be able to write our code in pandas. So if you're familiar with existing vector databases, you often write, with their APIs, and you're working with dicts in Python, and it's not classical data science. Let's say we're not working with pandas data frames that we use to store our data and read and write pandas data frames. But in this case, we will. So that's how it's going to be a bit different. We're going to work with pandas data frames. So you can ask questions in the Q&A button above. Somebody asks already if there will be a recording of this. There will be. And yeah, so you can write them in the Q&A, and then I'll get them as I see them popping up. Okay, so what are we going to do? Well, we're going to look at how to build a LLM application. We're going to do it just in Python. And it's going to be able to upload PDFs. So where are we going to upload PDFs to? Well, it's going to look something like this, but the actual application, let's jump to it and have a look at it. It's a Python UI, so it's Streamlit. If you've heard of Streamlit, this is kind of what it is. And I just asked a question to it, tell me about bank supervision. And it gave me a big answer, and you can see it's got some hyperlinks back here. It gave me an SMTP refuse because I forgot to put in an email address in here to send the answer to, but that's fine. That's normal. And basically, you can see there's links. We get references to the answer it gives me, and these references are to PDF documents. And you can see the references to a Google Drive doc. So what I'm actually using here is I'm using Google Drive as the source for the PDFs. We're going to write a program which will take the PDFs that are in this Google Drive. It's going to what we do say is we're going to extract the text from it, create chunks of text from that PDF documents. And we can see different policies. You could do it by page, by paragraph, by sentence, as I mentioned. And we're going to then create vector embeddings from that text and store it in Hopsworks Feature Store in what we call an ANN index, an approximate nearest neighbor index. And then later on, when we want to make queries here, we'll see that we'll be able to issue the queries in the Python application, and we'll use that ANN index to find similar documents from the ANN index. But we're not done. That's what we call retrieval augmented generation. The second thing we're going to do is we're going to create a finely tuned or fine-tune a Mistral 7 billion model from the same PDFs. So what you can do is you can see the way we've got a nice answer here saying references here, and then we've got this list of references. You can get it to very consistently respond in a kind of in a consistent manner. Often you can do that with prompt engineering, but it's often a bit more work. Okay, so let's get cracking. So I should add, this work is inspired by a couple of students that I taught at KTH, Matteo and Federico, who indexed my lectures at a course that I taught in KTH, and you can ask questions. Now, they use an open source vector database. They did use Hopsworks as well. And what we did is with 3.7 Hopsworks, we've this integrated feature store and vector database. It's really the feature store with an ANN index. We've extended it with it. We now have it all in a single system. It makes the code a lot nicer and easier. So I'm going to start by showing you where we have our PDFs. Now, the code is actually written so that you can store them on a local drive, but here we're storing them in Google Drive because it's nice, right? Google Drive is a nice place. Ordinary users know how to upload PDFs to Google Drive. It's pretty straightforward. What we'd like to do is when the files have been uploaded here, the PDFs, we'd like them to be indexed. That means we'd like a program to take those PDFs, chunk them, so we're going to extract the data from those PDFs, so the text from it, and then write it to our approximate nearest neighbor index. And we're going to do that in Python code. We'll call that a feature pipeline, and I'll get into that in a little bit. When will that feature pipeline run? Ideally, it will run immediately when you've uploaded a new PDF, or when you've deleted a PDF, we can remove that from the index. One of the problems with Google Drive, however, is that there is no event currently to say on new file added to Drive. Here are the available events that we have, or add-on triggers for Google Drive. So we won't be able to do that. It would be great if you use S3 as a store of your any S3 compliant storage, such as AWS S3 or Google Cloud Storage or Amazon, or sorry, Azure Blob Storage. They do have notification APIs. So you can get a notification when a file gets uploaded and you can run your program at that point in time. That's just an FYI. So this is what we're going to look at building, and the code is publicly available. I'll actually put it in the chat. So if those of you who want to jump directly to look at it, it's at the Logical Clocks repo, and it's LLM-PDFs is the name of the repo. So it's the organization, sorry, is Logical Clocks. I'm going to send this to everyone, hosts and panelists. So I'm not sure if I can send it to everyone. Looks like I can't send it to everyone, but you can see the URL on the screen here. So it's Logical Clocks /LLM-PDF. So the code is public. So what this code basically consists of is a number of programs. We can see we've got notebooks, 3 notebooks that begin with the number 1, another notebook, a training pipeline that begins with number 2, and an inference pipeline with number 3. And then finally, we have our Streamlit application, which is this app.py, and we've got requirements.txt, some packages we'll have to install. I'm not going to go through the pip, creating a virtual environment and pip installing the requirements. You'll have to do that yourself. But what we're going to go through is why we have split up the application into those different parts, the number 1 notebooks, the number 2, and number 3. But this is a way in which we encourage people to modularize AI applications. When I say modularize, we mean take it from one big blob program and break it up into smaller, more manageable components. And the way we do that typically with Hopsworks, which is the platform we're going to work with, is that we say what you have is a feature pipeline, which will take your data, and it'll, in this case, we want to extract the data from the PDFs. So we want to extract the text from the PDFs. We're going to compute embeddings on that chunks of text that we extract from the PDFs. And we're going to write that to the feature store. We're going to write it as a pandas data frame. So that PDF, or say that program to do it, is actually split up into 2 parts. We have one program, which is this feature backfill program, and another one, which is the feature pipeline. So the backfill one is when we have, let's say, a big drive with lots of documents, and we just want to load them all in. We want to create the tables, or what we call feature groups, where we store these documents in, and maybe add some metadata to them. So that's something you can run as a one-off thing. We can run it as a notebook, that's fine. But when we want to have a scheduled job, a job that's going to run on a certain cadence, then we're preferring to use Python. So we've got a Python program here, and that Python program will look for new files that are being added, new PDFs added to our Google Drive, extract the text, and then write the updated data to Hopsworks. The second one we have here is a dataset generation. So that dataset generation is actually creating the instruction dataset. An instruction dataset is training data for fine-tuning large language models. So there's many different formats out there for instruction datasets. We'll look at quite a simple one here, where we've got question and answer and some context information. But what we're doing here is we're actually taking what we call a trainer model. So we take the text that we find in a PDF, in a page, and we go and ask a really good model. In this case, a really good model is GPT-4, or you could try GPT 3.5 if you don't have access to GPT-4. Or you could even use a private model. So if you don't have any outside access, you might say, well, I'll go with Mixtral, which is a pretty good open source model, or the new Databricks model, which is quite good as well. And those trainer models will be able to generate these question answer pairs for you. So you can give it a page of data and say, generate 4 questions and 4 answers from this particular data. And then you might want to, generate a bunch of this instruction data, and then maybe manually you're going to adapt them to say, well, this is the actual format I'd like in my answer. I'd like you to have a reference here, and we'd like it to do this. But you can also do that in the instruction when you're telling the trainer model to generate an answer, you can tell it exactly how to format its answer, and then assuming they're all consistent and you've gone through all of this fine tuning data, all looks good, then you can fine tune your model. So we did this for Mistral. So Mistral is a 7 billion parameter model, and we quantized it to 4 bits. So it's actually, the size went down quite considerably from over 9 gigabytes to 400 megabytes. So it's not a huge model, relatively speaking, but it performs quite well. So finally, we then have an inference pipeline I'll go through, and the inference pipeline will take our fine-tuned model that we've trained on the instruction data set, and this is supervised fine-tuning, of course. And then it integrates with the feature store. So it's going to go to the feature store to find similar documents to the query that the user asks, and then we'll give back a response with, we think, the best answer to the query based on the content of those PDFs that's been extracted from the ANN index. So that's basically what we're doing. And there's one last step here, which is response logging. So when you have a production system in place, what you really want to do is collect the queries and the responses so your system can get better over time. And these can become what we call evals. They can be really good for identifying performance problems with your LLM. And they can even become new fine-tuning training data, depending on how you want to do those. But it's very important to collect them so that we can monitor the performance of the system. So this is what we're going to go ahead and do. And if you go to the GitHub repo here, we'll see that there is a little bit of overview, not a huge amount. There's a feature pipeline. We'll look at that to begin with. It's going to download new PDFs from Google Drive, extract chunks of text from the PDF, store them in a table or feature groups in HopsWorks, and then we use GPT to generate the instruction set. That's actually this part here is not part of the feature pipeline as such. It's actually going from the training pipeline. So this is what we call a training data set creation pipeline, or training data pipeline. So we often call these pipelines after the assets they produce. So a feature pipeline will produce feature data. In this case, it's the embeddings and metadata about the PDF documents. But the instruction data set is a training data set. So that's something we're going to use to train the models with. So we call that pipeline a training data set pipeline. And then the training pipeline itself will use this instruction data set and LoRa to fine-tune the open source model. This is Mistral 7. And we're going to save that back into HopsWorks. There's a model registry in HopsWorks we can use. And then finally, we have an inference pipeline, which is, there is a notebook as well that we can use to test out the model we've trained. But the inference pipeline that we use, we're running here, is a Python application written in Streamlit. And we added this email capability as well earlier, I mentioned here. So, I can write in an email address. This is me here. And then we can go back to our PDF and we can just pull one open here. Let's see. Not all of these are private data, actually. So some of them are public. But let's say, FinCEN's final rule on CDD. I have no idea what that is. But, I can ask my LLM. That's the whole point of it, right? So tell me about FinCEN's final rule on CDD. So we got an error. Maybe I have to restart this now. Oh, I'm out of error, queued error. So this is great. This is quite a typical thing that will happen in live demos. So I ran out of memory. It's telling me the GPU I'm running it on basically it didn't have enough free memory. So I'll need to restart that to get that working later. Okay, let's go back and we'll get started on looking at the code. So we're going to start by looking at the feature pipeline where we extract the data from our PDFs and from the Google Drive. So this code is available here. I've just opened a Jupyter Notebook in HopsWorks to look at it. And we're going to start with this feature backfill particular example here. So This is a notebook, and you can see we're using a library called PDF2. There are several libraries you can use out there in Python that can read PDF files. And we're going to use the sentence transformer library from Hugging Face to compute the embeddings on the chunks of data or text that we extract from the PDFs. So in this case, we want to extract these from this Google Drive here. This is my Google Drive here. It's got an identity. And I'm using that identity. If we go back in here, you can see this is the ID of my folder. And I'm going to download then the data from that Google Drive into this data directory here. You can see it's here. Oops, I go in here. So this is it here. You can see I've downloaded the PDF. So this is what the program is going to do. It's going to download the files to my local folder from this Google Drive. Now this code here you'll find it in the, let me just minimize this. It's inside this functions directory here. We've got this connect to Google Drive. First thing we need to do is connect to Google Drive. So you do have to connect to Google Drive, you do need to have this credentials.json and client secret.json files in order to connect to them. But then the actual code, if we go back, we're going to download the files to the folder. They're in this PDF pre-process directory you can see here. So it basically, you can see here, it uses this credentials.json file to connect to Google. And then we try and download it to this directory. If it doesn't exist, we're going to create it. So this is the data directory. And we basically list the files in there. And for any new ones, we're going to, if there's no new files, we won't upload anything. But if there are new files, we'll return them. So effectively, we're using this data directory as a cache. So if all of the PDFs you've been downloaded to this data directory, we don't need to rewrite them back into Hopsworks. Okay, so at this point, we should have any new files in here. And what we're going to do is just loop through them and process each PDF. Now, this is where we have our first kind of hyperparameter comes in. We've got a file. There's going to be some text associated with it and a path. So let's have a look at this process PDF in here. This directory. We've got this process PDF. So we're going to store the PDF in this data directory here. We can see this is where we're using the PyPDF2. Oh, I'll zoom in a little bit, actually make this easier to read. We're going to use the PyPDF2 reader to read the files. We've downloaded it already. We're now reading up the file from the local directory, and we're calculating the number of pages. And what we're doing is we're going through all of the pages in this particular file, and we're adding the document text. So we're adding it by page. We now have a data structure which has the title of the file. We have this URL to our file, and then we have the page number for the file, and then the actual content of the page. So this is quite a useful data structure now we can use this to create a pandas data frame we'll see later. So this is basically got 4 columns. We have the title of the file, the URL to it, the page number, and then the page inside it. Okay. So we've done that. It's in our document text. And now what we can do is we can basically create a pandas data frame from it, because we have these 4 columns, and we give the name to the columns at this point. And when we create the data frame, we can pass the data in here. This is our list that we're passing in here. And this is our pandas data frame now at this point. We can see that we've got the file name, the URL to the file, the page number, and the text that was extracted. Now, this is chunking by page. And you may say, well, I want to chunk by column. And we do have some code in this repo for chunking by column, and you can contact us later, or sorry, by column by paragraph. You can contact us later if you want to go through chunking by paragraph, which would be a different policy that you might want to follow. So this is what we're actually doing here. I'm jumping ahead of myself, because this is what we're doing here. We're taking that page data and we're actually going to chunk it by column, by paragraph, excuse me. Process text data. So let's go back in here, process text data, which is not in there. It's in the process text data. It's in the text process Python file. So this is the process text data. We pass in our pandas data frame, and now we're working with pandas data frames. This is very familiar for a lot of data scientists out there. We can start out by saying, okay, we're going to apply the split page function to split the text into paragraphs. So this split page function here, we can see here, is defined up here. And it basically, we define a paragraph as having two end of line characters, one after the other. So it's basically going to split the data up by that, the page data. And now we're going to have paragraphs of data in here in the text column. And we can extract the paragraphs using this particular function here, get paragraphs. So that's what this is doing. And when we extract the paragraphs, we want to also store the paragraph number. So you can see here that we have a new column we've introduced here called paragraph, which will be the paragraph number within that page. So now we've got our data frame has been extended to include the paragraphs. We've got the paragraph text, we've got the paragraph number. We can clean up the data a little bit here. So, filter out rows where the length of the text is too long and, clean up a bit more here. But now what we end up in our data frame, this filtered data frame, is the file name, the file link, the page number, the paragraph number, and the text. So this is pretty straightforward, not super interesting, right? Processing PDFs mightn't be everyone's cup of tea, but the code is pretty boilerplate at this point. So now that I have my data in a pandas data frame and I'd like to insert it into my vector database, which is our feature store in this case, before I do that, I need to compute embeddings on the text, so the paragraphs. So if we go back to our diagram here, we're now at this point. We've extracted the text in our feature pipeline, and we want to compute the embeddings. So let's look at how we do that. Well, we have a question already from Magnus. Any tests done with structured text formats such as TEI would be interesting to see the benefits. And then you referred to project in Sweden. So there are many other text formats out there. So PDF is the one that I'm working with at the moment. But obviously this code can be easily adapted if we just take this PDF pre-processing and work with the TI format. I'm not familiar with that particular format, but I'm sure you can find a Python library or pandas library to help work with that data. But basically, it's just going to be stored in the data that you extract will be stored in our columns here. So then we're going to, before we insert that into the feature store that we see in a second, we're going to have to compute an embedding on that text. So if you have a different file format, you extract the text into clear text, and then we can just apply the same stages. So here, what I'm doing is I'm using the sentence transformer model to compute embeddings. This is the one that we're going to download, and we're going to use the sentence transformer from Hugging Face to download it. And in this case, I have a GPU. It helps to have a GPU to compute embeddings because it's going to be very slow if you run this on a CPU. So in Hopworks, how this works is that when I want to start a notebook, you can basically select as many GPUs as you want to use here. Now, I didn't select any because I'm just showing you the notebook. But if you have available GPUs, you can see I've got 2 GPUs free here. In this cluster, I could just start a notebook with the GPU, and they're shared amongst all the users of the cluster. So I'd have my GPU here, and I can go and compute the embeddings. So this is all we need to do to compute the embeddings. We call model.encode on the text column from our data frame, and we store the output in another column we're calling embeddings. Now we're going to create another column here called context ID, which is going to store all the values ranging from 0 to the number of rows in the data frame. So now you can see here, we've got our context ID, which is this ID of for each row. So effectively a row number. And then we've got our embeddings. And we can see the embedding here is an array of floating point numbers. So, one of the parameters that I didn't introduce here is when we call model.encode, you can define the dimension size of this vector, vector embedding. But there's a default size, which we went along with here, which is fine for our purposes here. Now, we've got a pandas data frame. How do we, make this available for similarity search? How do I store it so that I can now search for it? Search for similar documents based on an input query, user input query. Well, we're not using a vector database. We're using Hopworks feature store, which has vector database capabilities. So the code looks very similar to any Hopworks code you may have seen before. First, we log into Hopworks. We get a reference to our feature store. The difference here compared to what you'd normally do, normally you would create a feature group and insert your data frame. But when you have a column that contains an embedding, and we like to index that for similarity search, we create an embedding object here. You can see we've got this, we import this embedding module from HSFS. We create an embedding index. There will be a default embedding index in every project in HopSworks. If you want, you can actually define the index name. And now then we're adding our particular index in here. Now you can see here, this is a little bit of a hack saying I want to get the length, the dimensionality of my embedding will be the length of, this particular text inside my embeddings column. You can actually also call length on the with the model itself. So this our embedding model here. Where is it back here? This model here also has the dimensionality as a parameter. So you could have just called that in here. It would have been a little bit nicer. Okay. So now with this embedding object, I need to basically tell my feature group when I'm creating it. A feature group is a table containing our pandas data frames. Think of it as being incremental data for pandas data frames. You can keep writing and writing and writing or updating or deleting data frames, and then the data will incrementally increase in our feature store. So, when we run a pipeline every day or every 10 minutes to check for new PDFs, they'll keep getting indexed and new ones will keep getting indexed. And if you remove files, we can then remove them instead of calling this insert by calling delete on the data frame with the data we want to remove. So in this case, what we're doing is we're creating a feature group called documents FG, and we're saying that we have an embedding index here, and that's this one here, and we've added one embedding to it. If we had multiple embedding columns, we could call emb.add embeddings to the next column. In this case, we only have one. And in our case, the embedding feature groups that contain embeddings should be online enabled equal true. So the online data will actually be stored there's a backing vector database in HopSearch called OpenSearch that we're using to store this vector embeddings and to do similarity search. So what you do is you basically call insert on your data frame. It'll upload it to the platform. And then we can create something called a feature view in HopSearch, which is how we typically query the data from HopSearch. And you select those particular features that you'd like to use. Now, often what you might want to do is you might want to combine features from many different feature groups. Maybe you have information about who created the PDFs. Maybe you have information from a different table about policies relating to PDF documents. And you can do that and incorporate all of that in a single feature view. In this case, I just made it simple and selected the features from this feature group that I'm putting in my feature view. So let's have a look at what happened when we ran this. So in HopSearch, what actually happens was it created this particular feature group here. And we can see we have the file name, the page number, the paragraph, the text, the embeddings, context ID. So we have all of that in here. So it's 6 features in total. And you can see some provenance information. So where is this used? Well, it's used in our documents feature view. We could have add expectation rules from Great Expectations. If we wanted to validate the data as it enters, we could add alerts so that if there's a problem in our expectations, for example, or if the insertion fails, we can get an email or PagerDuty or Slack alert. And there's a bunch of things we can do around it, and we compute statistics over them by default. You can see, for example, in this, we have a context ID, which is a numerical feature. The embeddings, you can see we don't have a huge amount of statistics from them. Each one of the rows is distinct in this particular case. And then we have page numbers and paragraphs. So there's not a huge amount of information available in these ones. There's also support for feature monitoring, which is new to 3.7 version of HopSearch, where we can actually monitor features, particularly when you have a production model and you want to look for things like drift in feature data, and then you would enable monitoring. Now, there's another question here. This is the same one we had before, so I just said I'd answer that live and done. Okay. So that's we look now at what we call the backfill feature pipeline. This is it created our feature group. Let's move on and look at the feature pipeline, which would run daily. So this would be something, or not even daily, we could run it every 10 minutes. So this is basically, it doesn't need to create our feature group because it already exists. It's just going to log into HopSearch. It's going to connect to the Google Drive, download any new files, and then it's going to encode the page number or the paragraph number, and then with the data frame that we get back, we're going to insert it in TopString. So you can see the code's a little bit smaller. There's a little bit of duplication in the code. We could make turn this into one big program that we run once for backfill, but we then parameterize it to run for this operational mode or daily mode. But in this case, for didactic purposes, I split it up into two feature pipelines. So a backfill one and then an operational one. Now, the operational one, this is a Python program. In HopsWorks, you can run this program pretty much anywhere in any Python environment. So if you like to use, AWS Lambdas, or if you like to use Airflow, you could, rewrite this slightly as an Airflow job, or you could run it on, modern serverless frameworks like Modal, or even GitHub Actions is a way people often write them. In this case, I can also run it as a job in HopsWorks. Now you can see I actually ran it earlier as a job, and I got a little failure because I forgot to install a library. So let's have a quick look at running it again. That particular execution, I have it set up to run every 10 minutes. It basically told me that I forgot to install a library. So yeah, it says no module called sentence transformers installed. So I can actually do that in HopsWorks. You can go ahead and install libraries in here. Here I'm in the Python environment for this project, and I can install, for example, sentence transformers, and there's two versions of sentence transformers. I think one with a dash and one with an underscore. Let's do it like that. Sentence transformers. I never remember which one is which, so I can install that like this. And what's going to happen actually is going to build a Docker image now based on this Conda environment. This is actually a Conda environment in HopsWorks. We have a bunch of libraries in here, and this will build in the background a Docker image, so my job can run again with that new Docker image. Now, to create a job, I could create a new job. We'll call it like 10-minute feature pipeline. And I'm going to click on the advanced options. We're going to add a schedule. So we want to run it, let's say, I'm going to use a cron expression. Let's say we want to run it every at 2 a.m., but let's put it at 10 minutes past the hour at 2 a.m. So let's just do it like this. Let's run it at 10 minutes past the hour, at 20 minutes past the hour, 30 minutes, 40 minutes, 50 minutes. So it'll run it every 10 minutes, basically, this job will run. I think that's how I set the one up earlier. It's a Python job, so if I need a GPU, I'll give it a GPU here. Let's skip out of that. So that's basically how you can run a pipeline in the platform. And let's move on to the next step, which is the dataset generation. So we want to create, if we go back to our diagram here, we want to create this instruction dataset. So the instruction dataset we can see here is, I mentioned already, it's going to use a trainer model. So we're going to use the OpenAI as our trainer model. So I've imported the OpenAI library here, you can see. And we connect to HopsWorks. We create this feature view, which contains our documents. And what we're going to do is we're going to basically read those documents out as a data frame. So we've read them out as a data frame here. We don't want to include any rows that have too long a text column, so we just remove those. And then basically what we're going to do is generate questions from the text that's in our data frame. So what this particular function here is doing, generate questions. We give it an instruction. You can see our instruction here is that we'd like to have our formats back in a reply format in JSON, and it's going to have a format that looks as follows. Here are all our questions. Here are all the answers. And you need to also, when you're doing this data set generation with a trainer model, you do have to be explicit about the kind of things you say. For example, tell it, ensure that the list of question and answers are complete and properly formatted, and you can even write an exclamation in capital letters to indicate this is important. Do not include any additional information outside specified format. Otherwise, we won't get back data in the format that we can use for supervised fine tuning. So that's basically the prompt engineering that we do for that. And then we call generate questions on the input text. We get back our text and it generates it here. We create that as a pandas data frame. And what we're going to do is write it back as another feature group. So we're going to create another feature group. This one's called CQAFG, and we're going to insert our data in there. And that's the data that we can use then for fine tuning. So we create a feature view so that we can read that, containing 3 columns: context, questions, and responses. So let's have a look at that data that was created here. This is the second feature group, CQA-FG. And we can see we've got a record ID, the questions, the answers, and the context. And we can have a quick look at that. We can preview that data if we want to. Look here, we can see there's this answer here, and there was a questions. Here's one of the questions. And there was a context column as well. You can see there's quite a lot of detail in this. So quite a lot of text in these ones. And this is our context question answers instruction data set. And we can create a feature view from it, this CQA, that we can use to then read training data and fine tune our model. And that's the next notebook, which is this one, the training pipeline. And in the training pipeline, you can see that we're using some of the libraries from, we've got the Transformers library and Torch, and we've also got the parameter efficient fine-tuning library. Again, we're using LoRa, which is pretty much, or you can use the LoRa, QLoRa, which is quantized LoRa, the pretty, the most common frameworks that people are using for fine-tuning, for supervised fine-tuning. And there are a bunch of Hugging Face libraries that we're using here, like Supervised Fine-Tuning Trainer and Auto Tokenizer, and so on. Okay, so we connect to HopsWorks. This time it's a little bit different. We're not just going to connect to the feature store. We're also going to store our model in the model registry. So what we do now is just we connect to the feature where we want to read data. So we can call a function called get batch data. We'll get all of the data back as a data frame from the particular feature view. These set of features, context, questions, and responses, which we've written back to our feature group. And now we can basically, go through it and say, okay, let's generate a prompt for each of these records in the data frame. And we have this particular function here, generate prompt. And that's coming from the prompt engineering, which is in this functions folder here. So we've got prompt engineering file here. And if we have a look up here, it's generate prompt, is this code here. So it's a very simple prompt template here. It's basically an instruction data set, as I mentioned. The instruction is you are an AI assistant, specialized in regulatory documents, because we're interested in PDFs, in this case, from the regulatory space. And then your role is to provide accurate and informative answers. Okay, and then we're going to fill in the context from our, this is our particular instruction train data set that we downloaded, the context, and then the question. Okay, so that's our prompt. And, we were down here, we're going to call, we said get fetch data, we're down here, we generate our prompt, and then we have our prompts back here. So from this, we can create a data set from this dictionary that we have. And you can see it looks a bit like this. Have a look at one of the entries in here. We have the instruction, we have the context, which is quite long. We have our question, and then we have the response. And this was the response, again, that was generated by GPT-4 earlier. And this is the context from the PDF documents. So what we're going to use is Mistral as our base model. So Mistral is an open source LLM foundation model. And we're using not just Mistral 7 billion, but Mistral Instruct v0.2. And there's a bunch of different open source models you can use. And this one is quite popular. Mistral has its own tokenizer, so we're going to use that to take our text and tokenize it, because that's what we need to do before we input it. Now, I mentioned before that we're going to actually reduce the size of Mistral. So we're going to use some quantization techniques. We're going to use the bits and bytes library to do it, and we're going to load it in 4-bit. And we're going to use bits and bytes 4-bit. So we're quantizing our model then quite a bit, and we're not going to use 32-bit floating point numbers. We're going to go down to 16 bits when we're fine-tuning. And then we're going to go ahead and can use, in this case, the from Hugging Face, the auto model for causal LLM to get back our model. So this will download our model from Hugging Face. When we have our model, we configure it with the tokenizer. We set up our configuration parameters here. So LoRa, as I mentioned already, is a parameter efficient fine-tuning technique, and there's a bunch of parameters that you can configure here. I'm not going to go through them all in detail, but you can see we've taken these from some existing work, and there's a lot of places on the internet where you can share information about good configuration parameters for fine-tuning with LoRa. Apart from that, there's also when you're fine-tuning, There's some other techniques you can use, like gradient accumulation, which will reduce the amount of memory consumption that you need. So if you don't have a large GPU, you can potentially use that to reduce the pressure on your GPU for overhead. We're using the Atom optimizer, which does add a lot of memory overhead. There are some new techniques I've seen out recently that can potentially reduce the size of your optimizer. And then we just the classical learning rates, the warm-up ratio, gradient normalization, and so on, and how long we're going to train for, the number of epochs. So, these are things you can play around with quite a bit. There's a lot of great, particularly forums on the internet where you can share this information about what make up good training arguments for fine-tuning models. So then we go ahead and create the trainer and do our fine-tuning. And depending on how much data you have, this can take quite a while, and we'll need GPUs, of course. So, in this case, I don't have a huge number of rows. It's only 1,190. I do need a GPU, but it'll get done in a reasonable amount of time. Now, the last thing to do here is once we've trained our model, we want to save it. So in Hopsworks, we can, when we're running this code in Hopsworks, it will save it to the file system in Hopsworks. So this is something you need to be careful with. In Hopsworks, we can save massive LLMs because we're not uploading this model over a REST API. So you want to be careful with your model registry. If you're uploading that model over a REST API and it's 9 gigabytes, you're going to have challenges and problems. So in this case, I saved it to the model registry here. This is our Mistral model. And, I didn't store any metrics, so I didn't really evaluate it. But we can have a look at the model itself. In our file system, we can see that the serialized model is in the safe tensors format that Hugging Face support, and it's quite small. It's 412 megabytes, which is pretty good, right? Which means it's going to be a little bit faster when it gives you responses. It's not going to take up as much data. You can potentially run it on a smaller GPU to get, you will pay a little bit maybe in terms of performance, but hopefully there's a trade-off that's worth making. Okay, so that's now we've gone through the third part. We've gone through our training pipeline. We've stored the model at model registry. We're going to now look at the inference pipeline, how we make predictions. So let's go back here, and there is an inference pipeline just to show you how to do this. Now, typically, what you would want to do is you'll want to generate what we call evals. So some standard questions and answers, and typically, you might want to put these into a separate Python program. And use PyTest to check that the model answers questions in a reasonable format. You might want to make sure it gives you references, the hyperlinks are there. And every time you make changes to your model or make changes to your feature engineering, you run these evals to make sure that your model is working as expected. Often, you will want to have humans evaluate the performance of the model, not just have, some unit tests to validate the model. But the more tests that you can add, the more you can be, confident that your model will perform as expected, even after you've made changes to it. So in this case, what we do is in the inference program, we connect to Hopsworks again, connect to the feature view and the model registry. We download our model. Again, it's using, it's downloading it as a local file here, and we're using the sentence transformer because the input text will need to use exactly the same model to create our embeddings that we used in our feature pipeline earlier. And in this case, we just load that model again from Hugging Face and get the tokenizer from it. And in this case, you can see then we're going to use an LLM chain to a pipeline to take the user's query in and then generate the response for them. So here when we're trying it out, we have a simple prompt template, and we can put in some questions. We're using the Hugging Face pipeline, and we have the prompt template basically has the context, the question, and you store the chat history, because it's not going to be just one question. You'll get an answer, another question, answer another question. So you store that over time. And that was an issue I had earlier, and my memory exploded because my chat history had gotten too long. So we're going to put this together in this LLM chain object. There is also a re-ranker. So you can do this, and I didn't mention this earlier, when you get back responses from your a similarity search. So you put in some text, we encode it, we go to the feature store with the ANN index, we'll get back some candidates. We can actually re-rank them. So this is a model that you can use to re-rank them, to make them hopefully the ones that are more closely related to the query will then get ranked higher than the ones that are less closely related. That's a fast ranking, re-ranking model that we're going to use locally here in this Python notebook. So we end up with a question: what are the best risk reporting practices? And then we call this get context and source. So let's go and have a look at that code there. That's in get context. And so let's have a look. Let me see, it's in the context and source. It's in the prompt engineering one here. So we go down here, get context and source. So we get the user query comes in here. Then we have our sentence transformer to create the vector embedding from that query. We have our feature view here that we're using to retrieve the chunks from our PDFs that are closest to the nearest neighbors. So this is our vector database query, if you will. So we start out by the query comes in here and we say, give me the closest neighbors. And this is our user query, the transformer object, the feature view, and we want 10. So I'm going to get 10 chunks back from the feature store using similarity search. So get neighbors is up here. You can see the call, the way it works is that the query comes in, we create our embedding from that query, the question embedding. And then on our feature view, we call find neighbors, and we use 10 in this case as the number of neighbors or documents we're going to get back. Okay, so once we've gotten back those neighbors, we can re-rank them with the re-ranking model. And then when they're re-ranked, we can get back the context, which is here. It's basically removing, because we were returning paragraphs, we're basically just joining some of that text together to format it correctly to return it. And then we're going to get the source. So in this case, the source we're looking at, you can see we're looking at the URL to the PDF. We're looking at the name of the PDF is 0, the URL is 1, and then the paragraph number is 3, and then the page number is 2. So the second element in that list. Okay, so then that's basically how, if we go down again, that's basically how the queries are returning. That we get back our context and source, and then we call LLM chain invoke, and that makes the call on our model, which will return our output. So this is, again, using the lang chain to get back the response that will return out here. So the app itself is really just taking the same code, but putting a user interface onto it. We're using Streamlit to do that. So in Streamlit, Streamlit's a Python library, of course. We have pretty much the same code as before. You know, we connect to the Hopsworks, we get a reference to our feature store on our model registry, we download our fine-tuned model. So now the model is running inside my Python program. Another option in Hopsworks, apart from downloading it, is you can actually deploy the model. So there is model deployment in Hopsworks. I don't have any here at the moment, but it's using kserve to deploy the models. So you can see here then, you know, because we have both the sentence transformer model, we have actually 3 models. We have the re-ranking model, and then we have the fine-tune model. They're all going to get downloaded into this Python program here. So this code is pretty much the same as we saw in the notebook. It's just turning it into a UI, and there's a little bit of you know, the user interface of these ST operations where you say, you know, chat message, and you can format the results as Markdown, and so on. So that's basically it. We've kind of walked through our whole application from start to finish, which is over here. I didn't discuss response logging, but that's basically writing your responses back to a feature group. But that makes up the whole of the system. It's available on GitHub, as I've seen already. So you're free to go ahead and download it and try it out. If you want to use it with the serverless version of Hopsworks, which is available at app or app.hopsworks.ai, so it's app.apps.hopsworks.ai. This will be upgraded probably by the end of next week, and with this new vector search capability. At the moment, it isn't there, so you'll have to wait, or you can go ahead and use the latest version of Hopsworks if you want to deploy your own Hopsworks cluster. But if you want to use this serverless version where you don't have to install anything, you just pip install the Hopsworks library, create an account here, and off you go. You'll have to wait until the end of next week for that. Thanks, everyone. Thanks for listening, and hope to see you all again soon.